Hi all, Raskas here. Let's talk about circular motion and gravitation. So for such a small unit on the AP, this list of subtopics looks pretty long, but I'm going to break it up into three groups of increasing importance. So let's get into it. Universal gravity. The first group of subtopics deals with fundamental forces, and the main takeaway here is that all of these so-called contact forces that we deal with at AP Physics 1 level when we're looking at mechanics, all of these forces, normal force, tension, friction, spring force, are really due to the interactions of electrically charged particles at the molecular and subatomic level. So the idea is these forces arise at the macroscopic level due to electrostatic forces of attraction between tiny particles, particles that have small masses and are very, very close to each other compared to objects which experience gravity. Now, all objects experience gravity, but what I mean is gravitational force is observed over larger distances, and the effects of gravity are most noticeable when the masses involved are much larger. So the next couple group of subtopics deals with this universal property of gravity, explains this in terms of equations, and this is usually an opportunity that the AP takes to assess your mathematical reasoning. There's also the idea that mass has a gravitational aspect to it, which is equivalent mathematically to its inertial property, but can be measured differently or independently. And then we'll talk about the perception of gravity. Now, under UCM, I broke that into kinematics and dynamics. Kinematics describing UCM, dynamics explaining it in terms of net force, free body diagrams, reference frames, resolving vectors, setting up systems of equations. And I'm going to do all of this as well as run through some examples of the three most common applications. So this is the equation for universal gravity, and we can see that it's an inverse square law. This is one way in which it's similar to electric force. However, each planet is going to have a different gravitational field strength, and that's going to be due to the mass of that planet. So if we look at the equation for gravitational field strength, it's Fg divided by mass. The mass that is being divided by is the mass of the object, the smaller object typically feeling the gravitational pull. And what we're left with is an equation for the gravitational field strength of a planet. Now, point to note here, small g varies directly with the mass of the planet and inversely with the radius squared. The radius here being the distance from the center of mass of that planet. So to give you an idea of how this is used, if we had two planets with the same radius but one had twice the mass, we'd expect that planet to have twice the gravitational field strength or twice the acceleration due to gravity. On the other hand, if we had two planets that had identical mass but one had twice the radius, the planet with the larger radius or twice the radius would have 1/4 of the gravitational field strength. Now, often in questions, they'll change both the mass and the radius at the same time, but this type of reasoning is what will get you through those questions. Now, can we feel gravity? The answer is no. We perceive gravity based on the normal force that is required to keep us still. What that means is if we are in a situation in which we are not experiencing a normal force, we actually feel weightless. And as we go through a couple of these examples of applications of UCM, we'll see how this is relevant. So when we look at the kinematics of UCM, universal circular motion means that you have a constant speed around a constant circle. That speed is tangential. That means it's going around the edge of the circle, but it's speed, not velocity, because the velocity is changing since there's a change in direction, and velocity is a vector quantity. Staying on the idea of speed though, that speed can be measured as distance divided by time. And so for one full cycle, the distance will be a circumference, the time is called a period, and so we get this equation v Tangential is equal to 2 pi r divided by period. Frequency is cycles per unit time, usually per second. Now, on to the idea of acceleration. There is an acceleration because velocity is changing due to a change in direction. This acceleration is directed toward the center of the circle and is given by v squared over r, where this v is the tangential velocity. Now, if there is an acceleration, according to Newton's second law, there is a net force. And this net force is called centripetal force. Centripetal force is not a force that you draw in a diagram. It's not a type of force. It is the effect of the net force. It's just saying that an object that is turning has a net force, has a sum of all the actual forces on it that is directed toward the center of the circle and given by this equation. So, on to dynamics of UCM, and this is really the meat of this unit. Again, the idea is that centripetal force is a net force. It's directed toward the center of the circle and is given by mv squared over r. In applying these concepts to a situation, you need to think about your reference frame. Ensure that you always align one of your axes to the inward direction, meaning directed toward the center of the circle, because that is the direction of acceleration and therefore the direction of your net force. By doing that and resolving all your actual forces into that reference frame, you can sum your forces in the in direction, and that will be equal to your net force, centripetal force, mv squared over r, and your sum of forces in the perpendicular direction is equal to 0. And what that means is you can solve for forces in that perpendicular direction. So the strategy, general strategy for these questions would be draw a free body diagram. It's usually going to be in 2 dimensions because it's a circle after all. Choose a reference frame. This is going to depend on where the center of the circle is. You want one axis to be directed toward the center of the circle. Redraw your free body diagram if required to resolve the actual forces from your original FBD into components that are all aligned with the axes in your reference frame. Then those dimensions, those axes x and y, you want to analyze them independently. And again, in the y direction, which is what I call the perpendicular direction, there's going to be no net force. In the x or inward direction, the net force is going to be equal to mv squared over r. This is how you solve any problem for UCM. So let's look at 3 of the most common types of problems. First one, vertical circle and vertical force. A roller coaster, that's what RC stands for. We can see where the center of the circle is. What forces are going to act on this roller coaster? First step, draw a free body diagram. Of course, there's going to be gravity. It's acting down. Now, a lot of you are going to be tempted to write in a normal force acting up. Normal force is going to be there because it's in contact with a surface, but normal force is always a pushing force away from a surface. So that's actually going to be acting down. Now I put that in light blue because normal force is actually not necessarily there. It may or may not be there. Now the acceleration is downward, so our net force has to be downward. So if you think this looks weird, it's fine because all this is saying is that there are only downward forces, which means that there would be a downward acceleration, which is exactly what we need for this roller coaster to be moving in a circle. As for reference frame, we only have forces in one direction, so that's pretty easy. There are no forces in the perpendicular direction, so let's focus on the in, or what I call the x direction, even though it's vertical. In the in direction, our acceleration is going to be v squared over r, centripetal acceleration, so our net force will be m v squared over r. And so from our free body diagram, we can see that that net force has to be the sum of the actual forces, Fg plus Fn. Fn is in parentheses because Fn may or may not be there. In fact, Fn can go down to 0. That tells us that the minimum total force will be just Fg. And that gives us an equation for our mv squared over r for the minimum value of that, which if you think about it, the mass is set, the radius is set, so the only variable there that can change would be our v. So this is the minimum velocity required for this roller coaster to go around this track of this radius. Analyzing it further, we know Fg is equal to mg, and so we can cancel our m's and solve for v. And what we get is we need a minimum velocity equal to the square root of rg in order for that roller coaster to make it around that circular track. Pretty cool. All right, horizontal circle with a horizontal force. Now, if this is within a gravitational field, of course, you're going to also have a force of gravity. So you are going to have vertical forces and horizontal forces, but there are no forces at random angles. So we have a car going around a bend. We have gravity acting down. We have normal force acting up. And if this car is going around a bend, meaning it's traveling in a horizontal circle, our understanding of centripetal force tells us that this motion requires a force directed toward the center of the circle. That force would come from the force of friction between the tires and the car. If you think about it, if you go too fast, or if you have tires that are too smooth, or if you are on a wet road or ice, the car would not go around the bend, it'll skid outward. So there we have our forces. Our acceleration toward the center. What does this tell us about our reference frame? We choose the indirection as one of our axes, which means that in this case, there's no need to resolve any forces. We can go ahead to our analysis. So analyzing in our x direction, we know our net force is going to be equal to mv squared over r, and our net force is only friction. That gives us this equation. In our perpendicular direction, there's no net force, which allows us to equate Fn and Fg. Fg, of course, is mg. Bringing this together, we know that force of friction is equal to mu times Fn, and Fn we just said was equal to Fg, so we get this relationship. We have m's on both sides of the equation. We can cancel those, and we get this result, which when we simplify for v, we find v is equal to the square root of rug, r mu g, where mu is the coefficient of friction. Physics joke. All right, final one, conical pendulum. Conical pendulum is a horizontal circle. The circle is horizontal, but there is no horizontal force. Instead of a horizontal force, there is a force at an angle. In this case, it's a force of tension. That angle is drawn in this diagram as between the string and the vertical. So we need to pay attention to that. All right, so reference frame. You said vertical, horizontal. You're right, because that is going to align one of our axes, in this case the horizontal, with the direction towards the center of the circle. So we're going to replace ft with components in x and y. Ft in the x direction is going to be sine because it is opposite of the angle, and in the y direction will be cosine. Analyzing in the indirection, we know from our free body diagram our net force is going to be force of tension in the x direction, which is Ft sine theta, and from our knowledge of UCM, that should be mv squared over r. In the y direction, we can equate Fg and Fty, which gives us mg is equal to Ft cosine theta. Now what we have is we have two equations with some of the same variables. There's m in both equations, there's t in both equations. You can make one the subject, make m the subject, for example, and substitute, or you can do a little trick, which is to divide one equation by the other. And what you get is ft's are going to cancel, m's are going to cancel, and you get the neat result of tan theta being equal to v squared over rg, or v being equal to the square root of rg tan theta. So I hope that was as fun for you as it was for me, because of course physics is fun.